everyone, and welcome to another episode of Interstigation. In today's episode of Interstigation, I will go over the inverse derivative, which means that our section of exponential differentiation and logarithmic differentiation is done. And let's get started with our probably the last logarithmic differentiation daily problem. So the problem states that find the derivative of y with respect of x given this equation over here, and obviously we can use the property of logarithm to break this up. However, when we're doing this, we need to be careful because when we're doing this, we're assuming that x and y are positive numbers over here. Because if you have this thing over here, then the domain of both x and y are positive. However, over here, if both x and y are negative, we have a way of just multiplying negative numbers to get positive, and that could still be equal to 2. So this problem that we are actually dealing with is fine. We don't have to do any more because you will see that the graph would look like this because it has an xy, so it definitely has some elements to rational functions. So the graph would approximately look like this. Well, you can see this is symmetrical, rotational symmetrical, and we can see that we don't have to deal with anything else. If we differentiate this equation, it will be the same, this equation, even if it is in the third quadrant. And we can use implicit differentiation that we went over a long time ago. So we need to take the derivative of both sides. So take the derivative of both sides. Obviously, the right side is just going to be 0, and the left side, we need to use the logarithmic differentiation over here. So that will be 1 over, we have is ln of 6 times, we have is x. And we need to plus, so that is the sum rule. We can have 1 over. Notice over here that we actually need to use the chain rule over here. The chain rule states that we can add, so the derivative with respect of y of this log of 6y, and we need to multiply it by the derivative with respect of y over derivative with respect of x, and that is equal to the derivative with respect of x of 2, which is just equal to 0. And we can clean it up a little bit, so we can let this derivative of y with respect of x is equal to a, and this is what we actually want. So cleaning that a little bit, we have the ln of 6 times x times this thing would be 1 over this ln of 6 times y, and what we have is times a, and that is equal to 0. And we can move this portion to the right side of the equation, and we will be getting a over ln of 6 times y is equal to negative 1 over ln of 6 times x. And if we cross multiply, we get that is negative a times ln of 6 times x is equal to ln of 6 times y. Obviously, we can cancel these out because it's just constant and they're equal. We have the a is equal to y over negative x. Obviously, you can write that negative before the fraction. So a is just equal to y over x. And also, you can check this with explicit differentiation as well, but that will be way more complicated, and implicit differentiation is a lot better in this case. And today we are going to try to derive how do we differentiate inverse functions. So the inverse derivative basically wants to find the derivative of f of x, given that we know, given the derivative of the inverse of f, and we want to find this. Well, for convenience purposes, because this looks very daunting and confusing, for convenience purposes, we can let g of x to be equal to f, the inverse of x, and we want to find the derivative of f. And over here, we actually need to get an identity that f of inverse of x, the composite of this function with f of x, is equal to x. That is a property of inverse functions. If you don't know what inverse function is basically just switching x and y to get a new function. Well, the new equation might not be a function, and if you see this geometrically, it is just going to be, if I have a parabola over here, then its inverse is just going to be a parabola like facing right, and that is not a function, but geometrically you can see that it is reflecting over y is equal to x. And this property is true according to inverse functions. And we can rewrite this thing to be g of x, g of this thing. And you will see that why I reviewed implicit differentiation today. It is actually because we actually need it today. So that is, we can implicit differentiate both sides. So like this. Obviously, the right side is going to be simple, that is just equal to 1, and the left side, we are dealing with the chain rule again, so we need to find the derivative of g, so this, with respect of f, and multiply it by the derivative of f of x. And we basically need to find this thing, and it is obvious now that this, what we want to find is just 1 over g prime, the derivative of g of f of x. And obviously, if you just want to write it in terms of all of f, yes, you can. You just have to write it something like this, but it is really not that complicated, and you writing it like this really overdoes things that aren't necessary. So thank you for watching this episode of Investigation, and in the next episode, I will go over all of the inverse trigonometric functions and find the derivative of those. And stay tuned for that. Goodbye.